Hi, and welcome to the second fundamental theorem of calculus. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This is chapter 4 out of Larson's 11th edition calculus text, obviously a calculus lecture. Still in section 4.4, the fundamental theorem of calculus, but part 3 of that section, the third lecture, second fundamental theorem of calculus. And I find that my students have a difficult time with this, and so hopefully I can help you while I'm helping them. Pay particular attention to some of the things that are coming. The second fundamental theorem of calculus states, if f is continuous on an open interval I containing a, then for every x in that interval, right, some interval containing a, any x in that interval, the derivative of the integral from a to x of f of t dt is equal to f of x. And I might change this a little bit. It would be better if we wrote times the derivative of x. Because that's what most of my students forget, is the derivative of the upper limit. Alright, let's look at some examples and see how this works out. If capital F of x equals the integral from 1 to x of t squared over t squared plus 1 dt, using the second fundamental theorem of calculus, I'm going to find the derivative. So the derivative of capital F, using the second fundamental theorem of calculus, I'll find that capital F prime is, take our function f of t, evaluate it at x, evaluate it at this upper limit. So that's x squared over x squared plus 1, and then multiply by the derivative of the upper limit. Well, the derivative of x is just 1, so I'll get x squared over x squared plus 1, and it all makes sense. But now we have something else going on, and it just occurs to me that maybe we should write this derivative differently. Let me see how I'm going to do this. The derivative of a to u of x of f of t dt equals a little f of x. That's not true. Let's make it correct. Little f of u of x times the derivative of u of x. That's what the second fundamental theorem of calculus states. And it's not necessarily obvious, these portions from the original definition. And I don't know why I didn't think of that when I was typing, but I should have typed this in. Let's see what's going on here. If capital F of x is the antiderivative from 2 to x squared of 1 over t cubed dt, my f of t is 1 over t cubed. When we find the derivative, it's kind of like a chain rule thing. So I'll have 1 over x cubed. That's not true. That's not true at all, because this should be an x squared. What I have written here, which I just covered up, should also be there. Boy, I tell you, I must be tired this weekend. I'm doing too many videos in a row. 1 over t cubed, well, in this case, I input x squared. So that's x squared cubed times the derivative of x squared, derivative of my variable limit. So that's 1 over x to the 6th times 2x. The x from the 2x and an x from the x to the 6th simplify and give me 2 over x to the 5th. Wow, horrible drawing there. This next one hopefully clears it up for you. If capital F of x is the integral from 2 to sine of x of 3t to the 5th dt, notice that f of t is 3t to the 5th. So when I find the derivative is 3. Okay, what's my variable? My variable is sine of x to the 5th power times the derivative of the sine of x. Well, that's 3 sine to the 5th x times cosine of x. And I'm going to warn you right now, for those of you in my online calculus class, this is an exam question. If it's an exam question, make sure you understand it. If you don't, hit me up for questions. That's it for the second fundamental theorem of calculus, part 3 of the section 4.4 lecture. Thanks for listening.